The benefits of science will be even more spectacular than we can ever imagine. I wanted to do something that is of long-range benefit to humankind. Practically everything we touch in our daily lives has been developed and improved through basic research. Science is taking us on an ever-accelerating journey into the future.
Please join me in welcoming to the stage 2026 ACS President Rigoberto Hernandez.
ACS 150 chemistry is everything. Feel the spark, yes, and everything.
Wow, I know I'm inspired and ready for today. Good evening and welcome everyone. I am Rigoberto Hernandez, 2026 President of the American Chemical Society, and it is my sincere pleasure to welcome you to the ACS Spring 2026 Lecture Series sponsored by the Kavli Foundation. The Fred Kavli Innovations in Chemistry Lecture continues to promote groundbreaking discovery and public understanding of the world's mounting challenges and how chemistry provides solutions. The ACS is grateful to the Kavli Foundation for enabling us to showcase the achievements of outstanding researchers in the chemical sciences. And today, we have the privilege of hearing from one such leader in our field. Tonight, it is a great pleasure to introduce Moungi Bawendi of the Massachusetts Institute of Technology. His research centers on the synthesis, characterization, and photophysical properties of semiconductor quantum dots and related nanoscale emitters, with applications spanning optoelectronics, energy conversion, and biomedical imaging. As a computational physical chemist myself, you might not be surprised that I have been impacted by Professor Bawendi's work. Indeed, at least 2 of my publications involve quantum dots, and would not have been possible had it not been for the earlier groundbreaking discovery and synthesis of quantum dots by Bawendi, Bruce, and Ekimov. And of course, my TV would also not be as bright without those QDs. The world is truly a different and better place because of his work. Professor Bawendi received his undergraduate and master's degree from Harvard University and earned his PhD in chemistry from the University of Chicago. Dr. Bawendi joined the faculty at MIT in 1990 after postdoctoral work at Bell Labs, where he first began studying quantum dots with Lou Bruce, with whom he would share the 2023 Nobel Prize in Chemistry. He is the recipient of numerous other awards, including the 2000 ACS Award in Colloid and Surface Chemistry and the 1997 Nobel Laureate Signature Award for Graduate Education in Chemistry. Please join me in welcoming to the stage Professor Moungi Bawendi. Thank you and congratulations.
Every bump, every reaction, science moving us to action.
Well, it's really my pleasure to be here this evening to close out this day at the ACS meeting. ACS meetings are places of intense discussions and a lot of collisions between people and the inception of collaborations across the world. And it's a wonderful place to be here in Atlanta today. So the story I'm going to give today is a story of the journey of quantum dots from its inception with the discovery of Louis Bruce and Ekimov and my role in the synthesis. And then I'll go through that and then how it developed into a technology and where it is today very briefly at the end. It's a story about curiosity becoming a technology and being a commercial product. And it's a story of how long it takes also to go from discovery to impact. It's a story of just having to do the work and keeping at it. So let me start that story then. Let me start by telling you a little bit about myself. So I was born in Paris a long time ago now, last millennium. And my mother was French and my father was Tunisian. And so as a result, as a child, we moved back and forth between Europe and North Africa. My native language is French. And in Tunis, people spoke French, so I never actually really learned Arabic. But nevertheless, I was in between 2 cultures. Eventually, we made it to the US. This is me as a 10-year-old in Orly in Paris, waiting to fly for my first trip to the US, to West Lafayette, Indiana, home of Purdue University, a wonderful place to grow up as a teenager. And but also Purdue, if you replace the first U with an E, it's perdu in French, and perdu means lost. And so when I arrived at Purdue as a 10-year-old, not speaking a word of English, I was utterly lost. And it's a feeling that I've grown used to. Because, you know, as a scientist, you're kind of always lost. You know, you're always questioning your intelligence in a way, because you're always feeling ignorant. You're always challenged by new problems which you have to solve. And if you're working at the frontier of science, you're working on problems that nobody's solved before, and you just have to figure out how to do it. So the feeling of being lost is a feeling that I grew used to from an early age, and I think it has served me well in terms of being able to deal with that. So after growing up, partly, we went back and forth between Purdue and Paris, and a few times as well. Eventually, I ended up at Harvard as an undergraduate, and coming from the Midwest, it was also a feeling of being lost. In 1978, coming to the East Coast and being surrounded by private school kids that I had no idea existed, And I had no idea there were such things as physics Olympiads and things like this, and physics camps, and I felt utterly unprepared for my time at Harvard. And so as a result, I promptly failed my first chemistry exam, got the lowest grade in the class. And so that was, it's not that I didn't know the material, it's that I didn't know how to study for the material, and also I was intimidated. But then I got over that pretty quickly. I learned to study, and then the rest is history, so to speak. So, you know, studying for an exam is not the same thing as doing research. Research is a very creative process, and learning to study for an exam is really about learning things that are already in textbooks, but learning how to deal with them very quickly so that they're right in your brain so you can access them quickly. And that's actually a skill that's important for research as well, because you have to have that background to be able to connect the dots. After Harvard, I went to the University of Chicago, and I was sure I wanted to be a theorist. I loved math, and I started to do statistical mechanics with Carl Fried, incredible mentor. And very quickly, well, after 3 years, I realized that even though I loved the math and statistical mechanics, there was a little something missing in that I was calculating thermodynamic quantities, but I really didn't have good intuition for what these things were. I could calculate delta G's and delta H's and all that stuff that our illustrious president, I'm sure, is comfortable thinking about, but as a graduate student, those were just quantities to me, and it felt like this was not, there was something missing there. So I switched to being a spectroscopist. Now I've taught thermodynamics now for 30 years, and every time I learn a little bit more, and I love the subject now, and had I known what I know now back then, I probably would have stuck to being a statistical mechanician. But nevertheless, so I became a spectroscopist, a small molecule spectroscopist, looking at small ions that are of interstellar interest. One of them, for instance, was H3+, the smallest polyatomic molecule you can think of, 3 protons and 2 electrons, a really important species in interstellar space as a way of transferring hydrogen atoms from one molecule to another. Very important for interstellar chemistry. And this was wonderful. I really loved the quantum mechanics part of it, and the experimental part, working with lasers and interacting with the theorists. But having grown up being a little bit of an outsider, not ever feeling like I belonged in a community, the problem that I had with being a spectroscopist of that kind was that it felt out of place for me. Because there was a very large community, I was part of a big community, and it felt a little awkward for me because I was shy and not particularly eager to be part of a large community. I just wanted to work for myself. And so when I spent a summer at Bell Labs, I discovered a new world, the world of condensed matter physics, of technology, and nanomaterials. And nanomaterials, that word didn't exist before when I was there. We called them little particles, nanoparticles, nanocrystallites, all sorts of names. And what I really loved about it was that nobody else was working on this when I met Lou Bruce. Louis was pretty much the only person in the US to work on this. There were people in the Soviet Union and a few people in Germany starting to work on this as well. So there wasn't yet a community, and I felt like every problem was a new problem, and every solution generated new questions. And to me, that was heaven. This was what I really was looking for in science. And so I stuck to it. And so after Bell Labs, I came to MIT, and I kept working on that. So since we're going to talk about quantum dots, these small particles, these little particles, what is a quantum dot? A quantum dot is a nanometer-sized particle of a semiconductor. So it's become sort of like the prototypical nanomaterial, a material that you can engineer to have different properties depending on the size and the shape and morphology, as you'll see. And it's become advanced enough as a material that it's been, that the concepts that we use in quantum dots have now been used for other materials, such as dielectrics and magnetic materials, and all sorts of other materials that are not semiconductors. The same sort of tools that we use to characterize and synthesize them are now used for all sorts of other materials that have also quite interesting properties of that size scale. And so in a way, these quantum dots were the beginning of a new periodic table, a periodic table of nanomaterials synthesized by chemists that we can then think about assembling together to have new properties. Any new invention, it seems, doesn't come out of nowhere, and often it rises out of the possibilities that are given by instrumentation. And in the case of nanoscience, the instrument that was really, really critical to the evolution are electron microscopes. Because nanoscience is about materials that are smaller than the wavelength of the light. So we can't use a regular microscope to see what we're making. We have to use electron microscopes. And this is one of my students using an early electron microscopes in my lab here. It's got a bunch of knobs. Today, electron microscopes don't have any knobs. They're just a computer screen like everything else. And so when you make a good sample, you can go to the microscope and immediately see that, yeah, this was a pretty good synthesis. We're making particles here that look all about the same. They're all about 5 nanometers in diameter. And so this use of this new tool was really important, and it still continues to be important as electron microscopes increase their resolution and their sensitivities and continue to be a really important tool in this world of nanoscience. So what about the quantum part? So the quantum part is, because these are small things that have electrons in them that because they're small and those electrons have quantum properties. So when we think of an electron usually in a circuit, like on a wire carrying charge, we think of a particle moving around from voltage being put across your circuit. But as you know, if you take an electron and you put it in a molecule, it doesn't act like that at all. If you have an electron in a bond, quantum mechanics describes what it is. That electron now belongs to all the atoms in the molecule. It forms the bond between atoms. And this is the same thing. If you put an electron in a little box, it's no longer described as a particle zipping around. It's described as a wave function. The electron is there all the time, everywhere. It's not moving around as we think of it using classical mechanics. And so we have to think of it as a wave. And we know a lot of properties of waves, okay? And that little box is the quantum dots, is the small particles that we make synthetically as chemists. So those are the nanoboxes. And so when we have a wave, we are used to waves. For instance, we know about sound waves, and we know that the sound or the pitch of a sound wave depends on the cavity that generates the sound. For instance, if you have a piccolo or a flute, you know that the flute is a bigger cavity and it carries a bigger, longer wave, sound wave than a piccolo. And you hear that with your ears. You hear the lower pitched coming from the flute than the piccolo. The same thing happens with organ pipes. And this is a photo I took from the renovated Notre Dame in Paris, where they did an incredible job of renovating it so quickly after the fire. And it just shows that, if you have the will and the money, you can do incredible things, right? So these organ pipes, these beautiful organ pipes in Notre Dame in Paris, come in different sizes because the small ones have higher pitched and the big ones have lower pitched. And I've color-coded them here with blue for higher pitched and red for lower pitched, just like we have for color and electron and light waves. So we're very used to this. So our quantum dots, or little boxes, are nanoboxes for electron waves. And so, but how do we put an electron in there? Because I'm talking about a single electron, right? And these boxes have lots of electrons in them. So, but all these electrons are in these because these are full of atoms. All these electrons are tied up next to the nuclei, or they're used to make bonds between the nuclei and the crystals that fills up these boxes. So we have to liberate a single electron to make it an electron in a box. And how do we do that? Well, we do that in a very similar way as you would create a sound wave, let's say using a guitar. You pluck the guitar string, and you give energy to that string, basically, and then sound comes out of it, right? The energy from plucking the string becomes sound. Here, the energy that we give is blue light. We have a blue photon, we excite the particles, and we liberate one of the electrons from the sea of localized electrons and liberate it to occupy the entire box. We call that in physics a carrier. It carries charge. And that electron leaves behind a hole, or where it used to be. And it's that one electron then that creates the wave that eventually we see as color coming out. Because eventually that electron wave finds where it came from. It finds where it came from, and when it does, it liberates the energy, and the energy that it liberates depends on the size of the wave that it was. And so the small particles with the bluer waves, or the smaller waves, end up emitting bluer light, and the big particles that have the longer wavelengths end up emitting redder light. And you see that in fluorescence from these samples of quantum dots, these synthetically made particles that are little nanoboxes made with one electron in them. Okay, so the Nobel Prize was given for the discovery and the synthesis of quantum dots. And so this is also where the journey of curiosity comes in. Lou Bruce and Alexei Kimov were awarded the prize for the discovery of the effect. And they were motivated not by wanting to create a new technology or commercializing a new display, which they had no idea that was going to be the case, 30 or 40 years later, but by some really fundamental curiosity about the world. So Alexei was interested in colors from stained glass windows. It was already known that the red in stained glass windows, old stained glass windows, comes largely from small particles of gold. The Greeks already used that to make red-looking glass. So Alexei was interested in figuring out what about the other colors, and so that led him on a journey to create glasses that only had a few elements in them, elements that he thought might be part of providing this color. The first one was copper and chlorine. And by melting the glass and processing it under different conditions, he found that depending on the conditions, he ended up with different spectra, different colors, basically, but with the same elements in there. And he made the hypothesis that this was due to having different sized particles. He used small angle X-ray diffraction to correlate in the size of the particles in these glasses with the color that he was seeing. And he wrote a paper in 1981 with the first three words, quantum size effect, explaining that the difference in color, the correlation in color and size, was due to this quantum effect of what we now call quantum dots. Lou Bruce was working at Bell Labs independently on the other side of the Iron Curtain, because this was when Russia was part of the Soviet Union. And he was interested in measuring how fast an electron inside a semiconductor, a carrier, would make it through the interface to an electrolyte to give that electron to a molecule to do photocatalysis, so to do photochemistry. This was a time soon after the energy crisis of the 70s, and there was a lot of interest in using the sun to create fuels, kind of like today. This was the birth of the National Renewable Energy Labs, which today has been renamed the National Lab of the Rockies, because renewable energy is a forbidden word in this climate. But in any case, his interest was measuring the kinetics of that electron going from inside the semiconductor to create a fuel on the outside. And there was a new tool that had been created. Yeah, the importance of tools is really important. Yeah, is really critical here. This new tool was a picosecond laser, a laser that had pulses that were very short in time. Today, that seems really long with femtosecond lasers that we use routinely. But the picosecond laser was being used at Bell Labs at the time, and he wanted to use that tool to measure how fast the electron was moving across the interface. And because this was an interface problem, he wanted to have much of an interface as possible, meaning he needed a very large surface to volume ratio. How do you get a surface to volume ratio that's as large as possible? You make your material as small as possible. And so he ended up making cadmium sulfide particles smaller and smaller, using techniques that had been first developed in Germany in the context of radiochemistry, and discovered that depending on how he processed his cadmium sulfide particles, he also would get different colors. He had access to electron microscopes at Bell Labs and used those then to correlate what he was making synthetically in a solution at low temperature in water at the time to what he was observing in the colors. And he also wrote a paper came out a few years after Alexi's paper, with the first 3 words, quantum size effect. Science was ready for this discovery, right? Across 2 different continents, across the Iron Curtain, the same discovery happening basically at the same time. For about 10 years, at Bell Labs and in St. Petersburg, which was Leningrad at the time, the material was good enough to have seen the effect, but not quite good enough to really understand the physics, the detailed physics of it, and to use it for something. And so at Bell Labs and in Leningrad, then there was a lot of work to try to make the material better, to make the particles better, to really become a material that you could really do sophisticated experiments on. And that's where I come in. I come in because in '93, we wrote a paper on showing how to make samples that we could really begin to use to do physics on, because that was my interest. My interest was, when I started at MIT, my interest was not, I wasn't the only one with that interest, with that curiosity. The curiosity was, if you look at a bulk material and you compare those properties to the properties of the atoms, like if you take a piece of gold and you look at an atom of gold, they have properties that are completely different, right? If you take a piece of semiconductor, like silicon in a circuit, you look at its properties, those are completely different from those of a silicon atom. So what happens as you build up the bulk one atom at a time? Where do the bulk properties begin to emerge? When can you say that you now have a piece of bulk as opposed to a molecule or an atom? That was the question that I was interested in, following that evolution of properties with a number of atoms. And every property has a different evolution, will evolve at a different rate. That's what I proposed to do when I started my job at MIT. But in order to do that, I needed samples. I needed samples that I could actually do the physics on. And so I'm going to travel back in time here with some transparencies, before we had PowerPoint, handwritten because I was a physical chemist, still am. And this was the state of the art when I was at Bell Labs as a postdoc. So the particles were made, I called it the micelle prep, but it should have been an inverse micelle. And this was really driven by Paul Visados and Mike Steigerwald and Bruce and Lewis. They were made in water, little water droplets surrounded by soap, and the outside was an organic solvent like heptane or pentanes. And then you added some cadmium ions in it, and so the cadmium ions went to where the water was. These water bubbles were defined by how much water you put in there. And then you added some, essentially selenium 2- to make cadmium selenide. And the size of the little crystals that you grew in these water bubbles, these little water droplets, depended on the concentration of cadmium and selenium that were there, right? So if you had a small concentration of cadmium, you made little particles. And if you had a large concentration, you made bigger particles. And the way I drew them back in 1990, as you can see, is very misshapen. In fact, these particles were highly defective, very large size distributions. But there was one innovation that Mike Steigerwald had figured out, was that the surface of these particles were still chemically active. It was like a polymer, it was a living thing. And then you could add and react to the surface of these particles essentially, you could essentially wrap them up in polystyrene, let's say. Little plastic surrounding them, and then you could use them and redisperse them in other solvents, and then treat them as big molecules. And when I got to Bell Labs, I was playing around with different solvents and different ways of trying to make the particles more crystalline, and I came upon a combination of phosphine and phosphine oxide that every now and then seemed to really work when you heated these very small particles. And they grew a little bit, they became more crystalline and more homogeneous. And I used this technical word on my transparency here you see on the top, when you don't understand something, and it doesn't happen all the time. The word is magic. There was some magic going on, and I had no idea what that was. And it happened enough times that I was able to begin to do some physics. And I could only make one size, one good particle size, every now and then, right? So then I got to MIT. And the magic of Bell Labs stopped being magic. In Cambridge, for whatever reason, we could never reproduce what I had done at Bell Labs. We could never make the high quality materials, that one size. And in any case, I wanted to see how size, the evolution of properties with size. So I needed to make more than one size. I had a proof of concept that you could probably make really high quality materials. So I looked back on what we had learned. What had we learned? We had learned that in order to make good samples, we needed to go to high temperature. And why? Because we needed to make the crystals as perfect as possible. So they needed to be annealed. And so I needed to go to as high a temperature as I could. And with organic solvents, that's about 350 to 400 Celsius. The other thing that I had learned was we needed to separate nucleation and growth, because that was a way of creating samples that were going to be quite more monodispersed, where the sizes were more all the same. And that was a concept that was already known in the 1950s by physical chemists, by Lemaire and his co-workers, that the separation and nucleation and growth for big crystals gave rise to size distributions that were fairly uniform. And so those two concepts sound, and we had to get rid of water because semiconductors, their surface are extremely water sensitive. And if you want to have something that's clean and not oxidized, you got to get rid of the water and oxygen. So those three things sound pretty simple. You're a chemist, no water, use nitrogen, do everything in Schlenk lines. High temperature, that's it's not so simple. That's also pretty simple. Nucleation and growth, pretty simple concept. But as many things, when you're starting in these new areas, it was all about the details. How do you do all these simple concepts and actually make it work? And that's where my students, Chris Murray, in particular Chris Murray, and David Norris, who was the physical chemist who was going to do physics on these things, helping out Chris, one of the secrets of success as a manager is you hire people that are smarter than you. And I was very lucky as a first year, professor to have Chris and David join my lab for that reason. And so, we figured out how to do this. And this is now transparency that's actually used a printer because now we have inkjet printers in 1993. And then, the high temperature, the uniform surface from these phosphine oxides, the nucleation and growth to give monodispersed sizes, the slow growth, extraction as a powder, essentially a powder of molecules, and a purification method. And this is now called the hot injection method. And this is what it looks like in a YouTube video from about 2010 or so. There's a soundtrack to this YouTube video, which is inspiring, and if you want to hear it with sound, you should go look it up. So you see the quick injection there giving rise to two little seeds that look orange at high temperature at 350 Celsius, which is what the temperature of this flask it has. And here, the student is taking aliquots. About 20 minutes went by without us really realizing it. And then you see the different colors as we're making different size particles. And then he's going to put a UV lamp on them and liberate that one electron inside the boxes, and then create the electron waves that then find their hole and give rise to photons of different colors. So we wrote a paper in 1993. This was my first paper at MIT. So I came in 1990, fall 1990, and it took us about 3 years for this paper to come out. And today, if we have an assistant professor in many places that don't publish anything for 3 years, we think something's not right. And, we have some doubts about their future career. But I wanted to wait to have a paper that was good enough, because I was a little bit of a perfectionist. And along the way, I had told Chris Murray, that the world didn't need another way to make mediocre particles. We wanted to really push this as much as we could. And there's a few words that are underlined. It was a simple way, and he gave particles that were monodispersed, meaning roughly the same size. It was a single reaction. Those were important words for the for the eventual commercialization, because if you want to make something and sell it, the cost of making it depends on the number of steps to make it. So the more steps, the more expensive it's going to be, right? It doesn't matter what it is. It doesn't matter whether it's a chip, a pharmaceutical, a car. The more steps you have to make a car, the more expensive that car is going to be. That's the cost. It's not how much you're going to sell it for. It's the cost of making it. It's an important distinction. Then there's the size-selective precipitation. This was a way of purifying the material. So we have this nanomaterial, this new nanomaterial, and you made in a chemical way. And just like a molecule, when you make a new molecule, you need to purify it as much as you can. In the molecule, you pass it through a column, through a gel, you crystallize it. You have all these tools, but we didn't have tools. So this was a tool that Chris essentially invented on how to do this, using concepts from polymer chemistry. And so what we had then was, you can see the absorption spectrum now has a bunch of peaks. Those peaks at higher energies are the harmonics of the wave. So we can see not just the fundamental wave, like in the flute or the guitar string, but also the harmonic waves, the shorter wavelengths. And then we saw for the first time, really, a nice clean emission, a color that was quite saturated, that came out from that electron directly inside the box and not from some defects. And the quantum yield, and I have this on the transparency, narrow and bright, it seemed really bright to me. The quantum yield was about 20%, and I thought, this is so bright. It's so much brighter than 0%, right? Which is what it was before. And then one of my colleagues in Germany, Horst Weller, told me, well, that means that 80% of your sample is something like, not so good. And he was right. And today, the material is good enough that the quantum yield is essentially 100% for the commercial material. Chris, in his thesis, showed that you could have exquisite control over the size. So on your left-hand side here, you can see a series of sizes from about 2 nanometers to 15 nanometers running through the visible. And the difference in these spectra, in successive spectra, is probably a handful or a couple handful of atoms that are added to the particle to make it a little bit bigger, so the wave of the electron is a little larger. And then you can see then the evolution of these harmonics as a function of size. So when you make particles, or when you make a new material like this, nanomaterial that is homogeneous in size, and you let it sit, you let it evaporate, the solvent, and then it creates its own, it sort of crystallizes into these supercrystals. So that's something that we found pretty quickly also, 93, 94, 95. This was the work of Sherry Kagan, and we could make these supercrystals, fairly large. And this has become an active field of study on its own. If you combine these different nanomaterials together, different shapes, different materials, and make crystals out of them, basically. You can study them and understand to see if there's new properties that come out from these crystals that wouldn't be possible from using atoms. This idea of a new periodic table here. Reminiscing here, we've got Sasha Efros holding David Norris's baby. Sasha Efros came from the Soviet Union, worked with Alexei Ekimov. He was a young theorist who became quickly our inspiration. As experimentalists, we're often inspired by theorists who can help us get intuition about the chemistry and the physics of what we're doing, and help us lead us to new experiments where we discover new things. And so Sasha Efros became quite an important person in this field. Okay, so now we're ready to do physics. So remember, my curiosity was, how do I look at the evolution of properties from the atom to the bulk? This is an experiment at 10 Kelvin, a low temperature experiment, and all these lines that you see here these are the excited state. These are the harmonics of the fundamental wave that I'm sitting here, right? So small particle is on this side here, and big particles here. And what you see is these harmonics coming together in energy as the particle gets bigger, as if the particle is empty, as if there's no crystal inside here. The electrons don't really know. That electron doesn't really know about the crystal that's inside the box. But eventually, when the box gets big enough, right around this area here, the crystal is large enough, there's enough coherence to the crystal, there's enough unit cells that are able to scatter the electrons coherently, that the electron begins to feel the inside of the box, the fact that there are actually atoms there, that the dots are not empty. And you get this avoided crossing here, which as a spectroscopist, we dream about. And that avoided crossing is what you see in the bulk material. So this is the evolution. We can then track the evolution of properties, this particular property with size, as this is where we start to see the bulk effect. And by here now we have bulk. There was a bunch of people, W. Murner, for instance, that started to think about seeing single molecules in the 90s, and I thought, if they can see single molecules, then we can certainly see single quantum dots. There's very large molecules. And then like molecules, dots were all different. So if we could use the techniques of single molecule spectroscopy, we should be able to learn much more about quantum dots than we do when we look at an ensemble sample. And so that was the beginning of looking at using single molecule techniques to look at quantum dots. And the first thing that you see is at room temperature that they blink on and off. They're interacting with the environment, and they're basically behaving like little sensors. This blinking is the dots charging on and off. So this is, and then if you go to low temperature at 10 Kelvin, you can start to see the spectrum of an individual quantum dot. Instead of seeing a broad spectrum, which is broadened by the ensemble distribution, the inhomogeneous distribution of sizes, then we can start to see vibrational structure. And then we can really start to understand, by doing single molecule methods at low temperature, we can really understand the evolution of really intricate properties of the material as a function of size. And so these single molecules are still being used widely today, and they're also used to understand the application of these materials as quantum emitters for potential use in quantum computing or quantum cryptography, for instance. Okay, so you do single molecule spectroscopy. This is a function of time here. The energy, you see a bunch of spectral jumps. So you understand then the charging process, these tryons. You understand how the charges in the environment affect electric fields that then affect the energy of the electron in the box. So the idea of nanosensors of the environment, and you can see the local charge dynamics. In the 90s, in the early 90s, there was another invention that eventually won a Nobel Prize. That was the invention of the gallium nitride diode, a blue diode. So when I was starting out in these materials in the late 80s, early 90s, there was a huge community of technologists trying to find a way to make stable blue diode emitters. You could make red ones, but you couldn't make blue. And there's an entire field of study devoted to zinc selenide as a source of blue diodes. And it worked really well at 77 Kelvin, but it just didn't work at room temperature. And we'd go to meetings where all these talks were giving on zinc selenide and how to try to get it to work at room temperature. And this guy, in Japan, working for Nichiya Corporation, essentially by himself, discovered how to make gallium nitride emit blue, and changed the world, right? And it got the Nobel Prize for it. And so when we got access to these wonderful new blue diodes, we thought, these are amazing, and they could really work well with our quantum dots, because all our quantum dots have, we weren't the only ones thinking about this, the community now that had been created, the quantum dots have an absorption which is really well suited for the emission of these blue diodes at 465 nanometers. We could excite all the different size cavities with the same blue diode and get colors all across the spectrum from that excitation, unlike dye molecules where you have to choose the excitation to match the absorption spectrum of the dye. And at the same time, the idea of making a core shell particle to make essentially an M&M structure where a higher bandgap material protected the quantum dot from its environment allowed the quantum yield to go up to the 80, 90, 100%. So the combination of this invention here, the blue diode, and the high quantum yield dots then gave rise to technologies. And the first one was in biology. The idea of using the quantum dots to tag cells as emitters, and the creation of the first company, Quantum Dot Corporation, in 1998. So you see, 10 years from 83 to 93, synthesis happens in 93, and by 98 now we're talking about commercialization. We could do some sophisticated experiments. This is an in vivo experiment looking at rare cells that can be labeled with 2 quantum dots, and then you can do a microscopy, in vivo microscopy, to look at that cell and see how it interacts with the other cells. You can do more sophisticated experiments. This is now in the shortwave infrared, where we're using indium arsenide quantum dots, aggregates of dots, and looking at the difference between a tumor environment versus a normal environment, and looking at the difference in the kinetics or the flow of blood in the tumor relative to the healthy tissue. That really shows you why it's so hard to get therapies into tumors, because there's just no flow, and so on. Those were hard experiments. It wasn't until we met electrical, and biology is the closest thing that we had to synthetic chemists, right? It wasn't until we started talking to electrical engineers that what became eventually the killer app started, which was to use these things for lighting and displays. Okay, and the creation of 2 new companies, Nanosys and QD Vision, which are now part of Shoei Chemicals and Samsung. And so the first product that used this idea of using a blue diode to downshift the color was a light bulb. This is right when LED light bulbs came onto the market, and they were really expensive, like $100 a piece, and they were too blue when the light wasn't particularly great. But if you put quantum dots on them, you could create more red, and they would be the light would be softer. And this was a great idea and a great product, but it was way too expensive, and so it wasn't the right place for the quantum dots, right? We can make it simpler today, but that's a different story. But the same idea, so this is QD Vision, started with the light bulbs. The same idea was to do it in displays, where the cost was less important. So if you replace the white LEDs in a TV at the time, and with blue LEDs, and then use the quantum dots to create the red and the green, same idea, then you would have a display that was more energy efficient, because you only made the color that you needed, and with better saturated colors. And Sony was the first company to come out with this in 2012, 2013 model. And I have still 2 of these TVs, even though I had to buy them from Amazon on sale. And they were over-engineered, and they were great. But they had cadmium in there, and that was a public relations problem. But Samsung saw this and invested quite a bit of money. And this was, sometimes you have companies that see something and they're willing to spend, they have the patience to actually develop the material and the vision to do it, and Samsung did, and they bought part of QD Vision. In fact, one of the things they bought was the trademark QLED. And if you look at this QLED trademark, if you remove the tail here, it becomes OLED, right? And LG was their competitor selling OLED TVs, and so now they could say we have QLED TVs. So this trademark here actually cost them tens of millions of dollars, just this part right here. But in any case, now they were able to make indium phosphide quantum dots, get rid of the cadmium of the public relations problem, and today they've combined the pixelation of OLEDs to make blue OLEDs that are now inkjet printed on top with quantum dots to make the red and the green. And the morning of the Nobel Prize, I got an email from Samsung Display asking me where I wanted my new television delivered and how big I wanted it. So that was a little, so it's in my office and it's quite large. There are other applications. You can use now the sun, capture the sun to make a single wavelength. This is applications in agriculture to change the blue light to red light, which plants like better, for instance. You can do other applications. For instance, here this is downshifting for night vision cameras. A simple application. You take an in-gas sensor that doesn't see the visible or the UV, you cover it with a thin sheet of lead sulfide particles. On the left side here, you have the camera has the dots on top, and this part here is the native camera here, infrared camera. There's a suitcase here that has a little UV tag on it to keep track of where it is. It's one of my collaborators, Frank Jaworski, and a student here, reenacting a scene maybe in Berlin in the Cold War with 2 spies exchanging some secret documents. And the secret documents are tagged with a blue LED, which is invisible to a night vision camera. And you can see as Frank takes that suitcase here, which is tagged and runs across, the night vision camera becomes blind to the UV without the quantum dots. So it's a very simple application. Lots of other applications, flexible displays, infrared cameras directly, solar cells. So where are we today? So today, what we've learned from quantum dots is how to create these nanomaterials, how to manipulate atoms at the size scale to make materials that have well-defined properties, and using chemistry to create those things. So not only semiconductors, but metals and semi-metals and magnetic materials and oxides, etc. The list goes on. And they can be made with many shells. They can be made hollow. The community has grown tremendously, and with very smart people all across the world that are now working in this area to make all sorts of materials. And combining these materials, this idea of this new periodic table, that we can combine things together and make hybrid materials with new properties, with real applications, with the displays being one of them, and this hot injection that I showed you, this video on a 50 milliliter flask. Today the dots are made in essentially the same way, except instead of being a 50 milliliter flask, it's a 3,000 liter container. And that little syringe is a big barrel connected with a bunch of tubes to the 3,000 liter container, and a valve that opens up and the whole barrel is emptied into that huge container all at once. It's really amazing to see. New applications coming up in quantum system and optics, electronics. So the world keeps on finding ways to make these materials more and more useful. A lot of people worked on this in my own lab, and then if you multiply that with all the groups working on this around the world, it's really a tremendously large community now that has been created in the last 30 years or so. It's really incredible to see. Funding has been really important, and I want to stress the importance of funding for fundamental science. We have an incredible system in this country where we take young scientists, like I was, late 20s, early 30s, and we give them a lot of money. And who gives them the money? It's the universities. So my startup package at MIT was really where I did all the invention, right? I couldn't write a proposal and say, I want to make these materials and all the same size with high quality, but I don't know how to do it, so please give me money, right? Only a university would be able to do that. I mean, they trust you. Universities are kind of what Bell Labs used to be. Bell Labs trusted the scientists to know what to do. Universities trust you that when you start out, you're going to figure something out. Once you have results, and you can go very early, quickly to the foundations, and they'll give you a lot of money to try to do things that you think that might be impossible. And then eventually, the government will take over and give you money, like the NSFs and the Department of Energy, which have been amazing to me through my career. The Department of Energy, NSF, have been really critical to funding my work. And eventually, the companies will come in when you see applications. And then you have a portfolio of funding that allows you to then survive, different times like we are today, for instance. So on this note, I want to thank you for your attention.
Please join me in welcoming back to the stage 2026 ACS President Rigoberto Hernandez.
This was an amazing presentation, and I am sure that and Professor Bawendi doesn't have a lot of time, but we might be able to take a few questions. If you can go to the mics at either stage left or stage right, we will take them in turn. As I see someone at the microphone. As someone warms up, let me just ask a quick question.
Yes.
You use temperature control. Yes. And you said how you went to high temperature, and we all know that at high temperature, the materials are going to go to an equilibrium structure, spherical, so the quantum dots are dots. But then at the end, you said, we're going to make them multifunctional, and we're going to have structure. How do we beat thermodynamics to get those structures?
Well, even when you're at those temperatures, sometimes you're not quite hot enough. And if you combine that with ligands, different kinds of ligands that binds to the different facets, you can recreate then different shapes, right?
With control.
With control, right? And so if you lower the temperature a little bit, they'll grow like rods or platelets. You raise the temperature a little bit, they'll become cubes. So temperature control and ligand control become really important.
Wonderful. So chemistry and physics together.
Absolutely.
I see now there are 4 questions. Now I'm probably going to have enough time to take the first 4. Will you take the first 4?
Yeah.
And we'll start right, stage left. I'm sorry, house left, which is you over there, and then we'll go back.
Well, first of all, thank you so much for coming. You're so inspiring to young students from all around the world. My question to you is not a technical one, but more of from someone that is inspired by you. But what are some habits, either in your daily life or in the lab, that have made you the scientist that you are today?
Okay, so I think the most important thing that I tell my students about, succeeding is to constantly ask questions. Be curious and critical as well. Just because somebody wrote something as a conclusion doesn't mean that it's completely correct. And how did they get to that? And why did they say that? And so when you have data, what does it mean? And what's the next experiment? And how does that laser work? So all these questions, are constantly on my mind. And then the other thing that's important to me is to take time off. I like to do things outside of the lab. I like to go skiing and rock climbing and all these things, and I found that tremendously important to me.
Thank you.
Thank you. House left.
Yeah, that was a wonderful talk, so thank you so much. So I have a question about this kind of idea you brought up earlier about these harmonics or these other kind of electronic transitions. So something I've seen in the lab or in the literature as well with something like indium arsenide, for example, is that you can make particles that have about the same level of size distribution, so pretty monodisperse, but some of them will have a lot of these extra electronic transitions beyond your kind of lowest energy exciton transition, and some of them don't. So I was wondering what your thoughts were on what the kind of fundamental differences between these two would be. Is it a defect thing, a structure thing, a surface kind of issue?
Yeah, well, without knowing the detail, it's really hard to say. If they're really good quality, really good crystals, then you should see all these extra things. And so, you have to go back and really understand their structure.
Thank you.
On the other side?
Fantastic talk. I really like seeing some of the history of the quantum dots. I have just kind of more of a for fun question. Of all the different quantum dot systems you've worked with, do you have a favorite?
Oh, no, you can't ask that question. It's like asking, which one is your favorite child?
Oh dear.
Oh dear. Yes. The one that we are quite interested in working on today are the perovskite quantum dots. But we're still working on indium phosphide and cat selenide.
Thank you. The last question?
Thank you for the really great and wonderful speech, and I think your sort of background is quite inspiring. I guess my question is kind of more general and kind of in the spirit of this event, since this is the 150th anniversary of the ACS. I wonder on your take on, I guess, since your paper was like in the 80s and then in the 90s, things sped up pretty quickly. I wanted to ask, what is your take on the next 150 years of your research and probably chemistry as a whole? And I guess as an extra question to end it off, do you have a favorite ice cream flavor?
Well, let's start with the favorite ice cream flavor. Chocolate. Okay, now that's done. The future will be wonderful. To me, that's very clear. And science will keep accelerating. Technology will keep accelerating and will be driven by curiosity as we've been in the past, and that'll remain incredibly important. And people will keep on doing science regardless of the conditions. People have been doing science for millennia, asking questions, figuring answers. Before we had government funding agencies, before we had any sort of society as we have today, people will keep doing that. Science will keep going on. So I'm very optimistic about that. I don't think humans really know the future with certainty beyond 3 to 5 years. I certainly don't. And we really don't know 10 years from now what technologies are going to be like. I think that's really strange. We have a vision for it, but the reality is we actually don't know what 10 years is going to look like from now. So 150 years, we can just dream, and it's going to be incredible.
If I may say, I know that regrettably tomorrow there will be challenges, and those challenges we'll be able to solve because of the science that we do today. And if we make those investments in basic science today, we'll be in a position tomorrow. And you showed, with some curiosity, you were able to solve some problems that we didn't expect because of the science you did before it. Thank you so much for what you have done for us.